Hey guys, and welcome. We're going to go ahead and walk through a little bit of PowerPoint here on pneumatic power. And some of these principles you should have seen before when we did our unit on hydraulic power. So let's get started. Okay, a little bit about pneumatic power. What we're going to learn is what pneumatic power is, take a look at differences between pneumatic and hydraulic power, some early pneumatic uses, the properties of gases, Pascal's law, the perfect gas laws, Boyle's law, Charles' law, Gay-Lussac's law, the common pneumatic system components, the compressor types, and future pneumatic possibilities. This video may have to be split into two, but we shall see. Okay, a little bit about pneumatic power. Pneumatic power is the use of gas flowing under pressure to transmit power from one location to the other. Gas and a pneumatic system behaves like a spring since it is compressible. Air is the most commonly used in pneumatic systems, although some systems use nitrogen. Pure nitrogen may be used if there's a danger of combustion in a work environment. So a little bit about the differences between pneumatics and hydraulics. Again, pneumatics uses compressible gas. It possesses a quicker, jumpier motion. It's not as precise as hydraulics. It does require a lubricant and are generally cleaner. It does not require, a lubricant and are generally cleaner. And often operates at pressures around 100 psi. Generally produces less power, which is why we don't see them being used in heavy machinery like we did with hydraulics. Some earlier uses of pneumatics, for example, were something you may recognize was a bellow. This was a tool used by blacksmiths and smelters, for people that work with melting iron and metals. And this essentially allowed them to blow air into the fire to make it hotter, right, or fuel the fire. Otto von Guericke also had a demonstration of pneumatic power, and he showed that a vacuum can be created if he put two hemispheres together held by atmospheric pressure. I believe he sucked the pressure out, he sucked the air out from those two hemispheres and tried to use some horses to pull it apart. So he's demonstrating the power of pneumatics there. Using a pump as well. He pumped the air out. Okay, America's first subway, designed by Alfred Beach, was built in New York City and completed in 1870, was only 312 feet long and 8 feet in diameter. It used pneumatics within its system, but unfortunately closed in 1873 shortly after. Some properties of gases. Gases are affected by three variables: temperature, pressure, and volume. So unlike liquid that we dealt with in our systems, although liquid obviously can be affected by temperature, typically in systems with hydraulics, we don't usually account for it. But gases have no definite volume, which makes these problems a little bit different. Gases are also highly compressible, as liquids are not, and gases are lighter than liquids. So a few things here, some properties of gases. Absolute pressure. So there's such thing as gauge pressure and absolute pressure. And gauge pressure is the pressure on the gauge of your system and does not account for the atmospheric pressure on all sides of the system. The absolute pressure is the atmospheric pressure plus the gauge pressure. So absolute, again, is atmospheric plus the gauge pressure. Atmospheric pressure is also known as barometric pressure, and it's the weight of the air molecules. An application of air pressure is when your ears pop. The pressure is balancing on the inside and the outside of your ear. And absolute pressure is used to complete pneumatic calculations. So again, absolute pressure is gauge pressure plus atmospheric pressure. Properties of gases here. So dealing with absolute pressure, P, it's measured in pounds per square inch, which we had seen before in our hydraulics unit. Standard atmospheric pressure equals 14.7. That's at sea level. Atmospheric pressure atmospheric pressure is lower at higher elevations because less air exists above to exert pressure, right? So as you go up in an airplane, what happens is there's less pressure the higher you go up because there's less air from our atmosphere actually sitting on top of you to exert. Similarly, atmospheric pressure is higher at lower elevations than sea level as well. A note of caution, reported pressure from weather stations is referenced to the usual pressure in that location, and the reported pressure is called the station pressure and is corrected for elevation. So the station pressure at the highest human settlements would be around 30 inches of mercury, 14.7 psi, while the actual barometric pressure is less than 7. Okay, so if a gauge reads 120 psi, what is the absolute pressure? Well, assuming that we're at sea level, that would be 120 plus 14.7, giving us 134.7 pounds per square inch. Okay, again, this is just a little bit of a graph that shows you atmospheric pressure and altitude. You can see as you are 0 in altitude, you have a much higher pressure. So this would be at sea level, right? And as you continue to climb up maybe a mountain or increase in meters, this is altitude in meters, the total pressure decreases, right? Because there's less air sitting on top of you. Notice that the total pressure is in kPAs in this case, which is a kilopascal. And the kilopascal is a unit of pressure, okay? And 1 kilopascal is approximately the pressure exerted by a 10-gram mass resting on a 1 centimeter squared area. Okay, 101.3 kPa equals 1 atmospheric pressure. That's just a different conversion. There's 1,000 pascals and 1 kilopascal, by the way, which should make sense. Moving on, let's talk about temperature. Okay, absolute temperature. 0 degrees Fahrenheit does not actually represent true zero. True zero represents the lack of molecular movement. Molecular movement increases as temperature increases. And for those that have taken chemistry or been through a little bit about chemistry, we know that, right? As we heat up molecules, they start to bounce around and move faster, right? Absolute zero is actually negative 460 degrees Fahrenheit. Absolute temperature, when we deal with our problems, is going to be measured in degrees Rankine. That's what that is, and we use the letter R to represent Rankine. And so degrees Rankine actually equals the degrees in Fahrenheit plus 460. A small application of this would be if the temperature in the air system is 65 degrees, what is the absolute temperature? So in order to find that, again, we can just take Fahrenheit and add 460, which would be 525 degrees Rankine. Again, pneumatics equations should use absolute temperature. That's why we're mentioning this. Okay, a little bit about Pascal's law. Pressure exerted by a confined fluid acts undiminished equally in all directions. Again, we know pressure is the force per unit area exerted by a fluid against a surface. And in this case, the fluids we're talking about are gases. So pressure is force divided by area. And these units for reference, once again, pressure is pounds per square inch. Force is measured in pounds. Area is going to be measured in square inches, at least in this instance. Okay, an example of Pascal's law very quickly here. To say how much pressure can be produced with a 3-inch diameter cylinder and 60 pounds of force. Well, we can look at our diameter, which is 3. We know our force, and if we want to find pressure, we are also missing area because pressure equals force over area. To find the area, again, this is a cylinder, so area of a circle, pi r squared. Our radius is going to be half that diameter, which is 1.5. Pi times 1.5 squared, and they're going to round it, is around 7.07. Of course, you should be plugging in the exact answer into your calculator when you figure this out. So 7.07 is truncated. And our formula is F over A. Our force was 60, our area was 7.07, and we get around 8.49 pounds per square inch. All right. So those are a little bit about some of our gas kind of formulas that we're going to be using. And what we're going to get into in our next video is some applications of the perfect gas laws. So we have Boyle's law, we have Charles' law, and we have Gay-Lussac's law. So I will see you in the next video, and we can take a look at some of the applications of each of these three laws.